Okay, so a different point that comes to us from the birthday problem, and this is a point about computation, about calculations that involve big numbers as intermediate steps. So I've asserted at this point that once we have 23 people, the probability that at least two of them have the same birthday is greater than 50%, but we haven't actually established that yet. Um, so if we wanted to look at that, it would be the probability that at least 2 and 23 have the same birthday. It's 1 minus 365 factorial divided by 365 minus 23 factorial times 365 to the 23rd power. Okay. And that number is, I think it's like 50.74. It's just over 50%. But if you go and try to punch that out on your calculator right now, or even plug it into R, you're going to have some problems if you just type it in like that. 365 factorial is a really big number. My calculator can't calculate it, and I don't think either R or Excel can either. Even this is, I guess, 365 minus 23, 342 factorial, 365, 23. These are really hard numbers to compute. And 23 isn't that big. If you get up to, say, 100 or so, you're really looking at some numbers that are going to be very difficult for computers, packages, calculators to handle, even though we know that the end result is going to be a number between 0 and 1. Okay, so how to handle this? This is where taking logs saves the day. All right, so the trick, and this is a trick that is used extensively in statistical programming. So the packages that you run, that some of you may end up contributing to, will often involve taking logs of complicated probability uh, functions. And the trick is to find the log of this probability. I'm just going to look right now at the probability of no two being the same, all different. So just this part of it. That is the log of 365 factorial minus, so that 365 minus 23 factorial is down here in the denominator. Let's just do the subtraction. It's 342 factorial times 365 to the power 23. And why am I taking the log? Because the log lets me take apart those big products and turn them into sums, and the quotients and turn them into differences. And the log is just going to bring down the values of all those really big numbers and in a very nice way. Okay, so this equals the log of 365 factorial minus the log of 2 factorial minus 23 times the log of 365. Okay, so just the log of something to a power, the power times the log of the thing. Okay, it's still, you're still thinking, well, I'm still seeing that big log 365 in there. Well, what is the log of this product? It's the log of 365 plus the log of 364 plus the log of 363, blah, 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 blah. So I can write that here as the sum as I goes from, let it go from 0 to 364 of the log of 365 minus I. Okay, so that's this term. So when I is 0, it's the log of 365. When I is 1, it's the log of 364, all the way down to when it's 364, it's the log of 1, 0. So that's this term minus the sum as I goes from 0 to 341 of the log of 2 minus I. So that's this little term here. Minus 23 log 365. Okay, so the biggest number in this calculation is the log of 365, which is around 6. Okay, nobody's going to have problems calculating that. And in part of your homework associated with this lesson, there's an R problem that's going to ask you to make a graph of those birthday probabilities as the size of the group increases. And it's even easier than you might think from this because R has a log factorial function built into that. I think it wouldn't be that hard for you guys to program that function if it wasn't there, but it's there, so we're going to use it. Okay, so I'm drawing your attention to this because this business of taking logs to manage big calculations, especially when they're intermediate steps here, is something that occurs a lot. It's a strategy that that you shouldn't be surprised by. For doing examples with the birthday problem, when you're looking at really small numbers, you probably can do it without using R, without taking logs, without doing the complicated thing. Just to be clear, the alternative is, say, what's the probability at least 2 and 5, at least 2 having the same birthday in a group of 5. Just writing it out like this: 365 times 364 times 363 times 362 times 361 divided by 365 to the 5th power. That's about, for me, the max of what I'd want to punch out on a calculator. But that does work. You don't have to do the factorials that way. And the probability that 2 and 5, actually it's 1 minus that. Okay. So that's 1 minus works out to be 0.9729. So it's around a 3% probability in a group of 5. Okay, so that's the birthday problem. As I said, it's a classic problem and has a couple of relevant things for us.